Now, Lindoranus, you can start with your.
Okay. Uh, Thank you, Kalina, for joining us. Thank you, Gamichu, for hosting this session. Uh, Today we're joined by Kalina. So Kalina is currently pursuing a PhD in computer science at the University of Utah. Her research focuses on cinematic scientific visualization, human-centered design, and AI-assisted tools for perception, interpretation, and trust. Until 2024, Kalina was the founding director of the Visualization Program Office at the National Center for Supercomputing Applications, or NCSA, where she provided leadership and management. Kalina was director of the NCSA Advanced Visualization Lab, which is an award-nominated team. As part of this team, Kalina personally contributed to films including A Beautiful Planet, Birds of Planet Earth, and Seeing the Beginning of Time. Kalina's background is in computer science. Earlier in her career as a research software engineer, she was one of the primary creators of Witten, an open-source middleware between the scientific analysis and visualization Python package YT and the visual effects software Houdini. She has also worked at the New York Times last summer and will work at Apple this summer. She is active in mentoring and advocacy efforts focused on diversity, equity, and inclusion. Kalina is also an educator and public speaker whose CV includes giving TEDx talks, teaching data storytelling in the Gis College of Business at the University of Illinois, Urbana-Champaign. Thank you, Kalina, for joining us. You may take the stage.
Great. Thank you much for the introduction. So I'm going to be talking to you about what most of my career has been about, graphics for science, or what I like to call cinematic scientific visualization. And I suppose I've already gotten a wonderful introduction, so I'm not going to go through my own background, but here are some places that I have worked and will in the future. So let's just dive right into the meat of the talk. So I would like to kind of situate this phrase cinematic scientific visualization, which probably doesn't mean much to anybody here, by introducing it in the context of some more familiar concepts. So the first related concept is visual effects. This is what you see in a lot of movies, often in science fiction films, but other types as well. Explosions, fire, electricity effects, magic. Those are often, very commonly shown in movies using these types of computer-generated imagery visual effects. The other related concept, which doesn't seem at all familiar, at all related, but I promise you is data visualization. So typically you might see visualizations represented as charts, as line graphs, bar charts. They're often used for data analysis. Cinematic scientific visualization, or my main area of research, sits in between these fields. So what I'm showing here is a planetary collision. And this is actually a data visualization. It's based on data from Dr. Robin Canup at the Southwest Research Institute, based on a numerical accurate simulation that she ran on a supercomputer. And it is created in visual effects software, features an explosion, and this was created for inclusion in a film. So cinematic scientific visualization is this combination of science and art and technology to create images that both entertain and educate the general public. These visualizations that I've worked on have been featured in all of these films on this screen. Many of these are available on streaming services. Amazon Prime, I know, has many of them, but they've also been distributed in immersive planetarium dome theaters around the world. So maybe you've seen one of these, or maybe you have a chance to. To kind of introduce some of this background and type of work that I've done, I'll play a short demo reel from the Advanced Visualization Lab, which until 2024 I was the director of. So I hope that the audio and the sound works. Let me know if there are issues, but here's a short video. So everything in that video was based on a real scientific data set, was a data visualization, but created obviously in a kind of entertaining, visually appealing way for including in documentary films and museum experiences, even sometimes for concert graphics. So that has been really fun to work on in my career. Creating these types of visualizations does involve quite a complex pipeline. Here's a graphic that I made at some point to try to show it all in detail, everything that goes into creating this. And obviously this is quite detailed and a lot of information and way too much to go into in a single talk. So I'm simplifying this pipeline into saying that creating this type of work involves solving 3 types of overlapping challenges. And I'll give examples from each of these 3 today. So the first is communication challenges. Visual science communication is challenging for many reasons. One of them is that these visualizations are created for general audiences. We are targeting everyone between ages of 8 and 80. So showing something that conveys the science accurately and is still understandable to both of these people with their different levels of education, different abilities, different interests, different language, is actually a real challenge. And I like to show this comic to demonstrate some challenges with communication. So here's a professor at a podium saying there is an eye at the center of a hurricane. And the first student interprets this correctly. This kind of middle part of the hurricane is called the eye of the storm, and that's what they are thinking. But the other students are interpreting this in very different ways. One is imagining a literal eyeball in the center of the storm. The other is imagining the letter I being in the center of the word hurricane. And these are both, reasonable interpretations once you kind of realize how this initial sentence was phrased. But even though you might think that you're communicating something, succinctly and accurately, it can still be interpreted in many different incorrect ways by your audience, which is a real challenge that we have to deal with. But sometimes there really is just no good way to visually communicate something as well. And I want to give an example with map making. So the Earth can be accurately represented as a globe, but oftentimes you want to show it in 2D as a map instead. And the Mercator projection is probably the most common way to flatten the globe. And that looks like this. But it misrepresents the size of land close to the poles. So here's the size of Greenland and what it would look like on different parts of this map. This is a fun application you could use, the truesize.com, to move around different countries. So this is not actually a very accurate interpretation since it's misleading about the actual size. But there are other representations. So let's look at a different one. Here is a different map projection that solves that problem. Now everything is the correct size. But we've introduced a new issue. Now Greenland, which we were moving around before, is cut in half. So half of it is on this side, half is on this side. So solved one problem, introduced another problem. But surely we can solve both of these problems at the same time, right? We can maybe come up with a fully accurate way to do this. Actually, it turns out we cannot. There are many, 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 many ways to visualize the Earth in a flat 2D map, and all of them are wrong in some way. There simply is no way to accurately show this unless you are showing it on a globe. So every map that you have ever seen is wrong in some way. And this is not just true for maps. This is true for all kinds of data visualization, for all kinds of visual communication. There often is a wide gap between numerical information, which might be correct, but then how we can actually physically display and interpret and understand that information. But projection issues aside, maps are a great way to present and display information. We see them all the time. Here's an old map of the United States where each state is colored by which party took most or all of its votes, electoral votes in the US 2016 election. And this is most commonly the type of visualization that you see. But it turns out that the map is actually not correctly showing the results of the election because the amount of red and blue ink on this map isn't proportional to the amount of votes that went to the red and blue parties. So Montana, which is highlighted here, is a very large state that adds a large amount of ink to this map but is very sparsely populated. Not a lot of people live there, even though it's very big. So that giant area on the map is only worth 3 electoral votes. New Jersey is a very, very small state, but a lot of people live there. So that state is worth 15 votes, even though it only contributes a small amount of blue pixels to the blue party. So we can remake this map to scale it, to stretch each state to actually represent how many votes it got, how many votes it received, and you can get a more accurate result of the election. So now Montana and New Jersey are rescaled so that they are the correct sizes to represent the actual result of the election. We can do this by county rather than by state, so breaking it into smaller chunks. So if we stretch that, now all of a sudden we get a very different story than who won the election. Now, this visualization is telling the story of how urban areas dominate the outcome of elections. So these large blue areas are the large cities. So here's Chicago, a very large city. This is Los Angeles. Here's New York. Now we see a lot more blue. So this is telling a very different story. Perhaps we could also say that looking at this, the country is very deeply divided. People with very different opinions are living next to each other. But if we visualize this yet a different way, if we color by the strength of a party's dominance rather than just who won, we see that there's actually a lot less solid red and solid blue. Now we're seeing a lot of purple. So we were able to tell kind of 3 very different stories with this data set, depending on how we visualized it. So one of the things I want to point out is that a lot of people think that, because it's based on data, visualization is necessarily accurate and objective, but really it is subjective. There's a lot of design decisions that go into it that affect what story is told. There's also a lot of subjectivity on how you as a viewer can interpret and understand that data. But in addition to just being subjective, it can also be unintentionally biased and problematic, or it could even be maliciously incorrect. Somebody that wants to tell us an incorrect story for evil reasons can actually do that with a visualization. And here's an example of one such, what I would call malicious visualization. Here's a simple graph showing gun deaths in Florida. And before I tell you what's wrong with it, I might want to throw it to you. Does anyone want to take a guess at what's wrong with this chart? Please unmute or post in the chat if you're more comfortable what you think is wrong with this.
Is it because the small number is shown higher?
Exactly. Yes. So typically in a graph, you expect 0 to be at the bottom and the numbers to go up from there. But here 0 is at the top and the numbers go down. So here it looks like there's a big drop in gun deaths, but that's actually misleading because it is an increase since this graph is upside down. So, in the United States, where Florida is and where this graph is made, guns are a politicized issue. And, this is a chart that could be using this data to be misleading about the number of deaths that are caused by this. So taking it back to, more, 3D graphics, here's an example that shows, 2 very different ways that a data set of a tornado could be visualized. So there's, on the left, we're seeing a more abstract representation. On the right is a more photorealistic one. And these are also telling very different stories. So the visual on the left is kind of more analytical and clinical. It's talking about the inner workings of the tornado. We can see how it forms, how the wind is moving, exactly what's happening. Whereas the one on the right conveys more of the emotion of a tornado being a powerful, dangerous force. It's kind of dark and brooding. So on the one side, the story is focused more on, educating and understanding, or on the other side, it's focused more on the emotion. And these are very different computer graphics techniques that are being used and different design decisions to drive these looks. So to make sure that visualizations are as accurate as possible, considering this wide variety of choices that can be made, we work very closely with scientists and involve them in the iteration process. So I'm a computer scientist by background. I'm not a scientist, even though I just showed you a visualization of tornadoes that I worked on. I don't know the first thing about tornadoes, other than their fast wind that goes in a circle. But by working with experts that actually spend their lives and their careers studying these things, they can identify inaccuracies long before they make it into the visualization and validate that we're communicating and conveying the science as accurately as possible. On the other side of kind of the communication spectrum, it's not enough to make a visualization that satisfies scientists. We also need to satisfy the audiences who are, complete non-experts in these subjects. So a lot of the work that I'm doing now at the University of Utah is focusing on audience understanding. We identified early when I was at the University of Illinois that audiences had a hard time telling apart the difference between photorealistic data visualizations, artistic illustrations, or photographs taken from a telescope. So by kind of asking survey questions like this and trying to talk to and understand our audiences, we can identify problems and work on solving them. So that was some examples of communication challenges. Now I want to move on to technical challenges, which is dear to me as a programmer background person, and the people that introduce themselves here also were computer science backgrounds, so perhaps this will be interesting to you all. You've probably heard the phrase big data. This is a problem that will never be solved because big data keeps getting bigger. What was big data 5 years ago is now normal data today. Big data 5 years from now will be something that we can't even wrap our heads around now. It just keeps getting bigger and bigger and bigger. So here's a picture of the Vera C. Rubin Observatory, which is kind of a telescope that captures data that produces 20 terabytes of data every single day that needs to be analyzed and collected and understood, and some of it visualized. Here's an example of a large data set that I worked with a few years ago. This is a digital elevation model, or a record of height, of every piece of land on the Earth north of 60 degrees, which is 1/6 of the globe, at a resolution of 2 meters per pixel. It took the scientist 1.5 billion hours, yes, with a B, on the Blue Water supercomputer to process and assemble this data set. And we worked with a subset of this data, not the full 200 terabytes, but we used 45 terabytes of data to create the visualization, which also took 110,000 hours on Blue Water's, the supercomputer, as well. One of the challenges with this data set and with data in general is that data is messy and requires cleaning and processing. So here's an example from this Arctic data set zoomed in onto one specific region where an ice cap is collapsing. And this was captured by satellite. And a problem with satellite data collecting information about the Earth is that there are often clouds in the way. And that's what these messy things that are popping on along the top image, this is where clouds came in between the satellite and the ground and got captured and were incorrectly represented as the height of land. When we started working on this visualization and wanted to recreate the satellite data in 3D, you see these terrible massive spikes that pop on and off, which is where there were clouds. This is, clearly not something you could put in a documentary film. This is terrible and ugly and distracting, but this is kind of where we started with from the raw data when we reconstructed it into 3D. Kind of after much processing with manual labeling, as well as developing a machine learning algorithm called Cloud Finder, which you can see a short paper about in IEEE Viz. We were able to remove all of the clouds and create a final data set that looks more like this. I'm going to play a video that goes into some of the behind the scenes of making this visualization.
Here's what went into making a piece of Atlas of a Changing Earth. We built on the results of the Arctic DEM survey project. That survey used high-resolution satellite imagery, hundreds of thousands of observations spanning several years, and measured the Earth's shape in fine detail, covering all the land north of 60 degrees latitude. Transforming that imagery into this mapped dataset of Earth's topography required millions of hours of Blue Water supercomputer processing. Satellite observations were in strips, a few kilometers long. Throughout the survey, many areas were observed on dozens of occasions, revealing how Earth's topography changes with time. This shot from Atlas of a Changing Earth animates the multi-year Arctic DEM survey in the context of a realistic-looking Earth. The visualization incorporates seasonal changes in Earth's appearance. We created it in layers. On the ocean is a climate model simulation of sea ice coverage. To design the unbroken animation path around the world and into Vavilov, we used AVL's interactive Virtual Director software. Virtual Director shows a simplified preview of the scene in the correct 3D location. Final rendered elements fit right in. Datasets, camera paths, and so on are brought into the commercial software tool Houdini from Side Effects. Its node-based architecture supports a mix of programmable and interactive design. The DEM survey data shows exquisite detail, but contains many artifacts, thanks especially to clouds. Seen in a 3D landscape, every defect becomes even more prominent. Lots of manual work went into cleaning the raw survey data, masking out clouds and aligning strips with each other. The DEM data was observed at discrete times at irregular intervals, days or months apart. To give the sense of continuous motion, we used morphing interpolation in Nuke on the high spatial frequency ripples in the collapsing Vavilov ice to create three-dimensional evolving topography. Here's what went into that. Starting from a flat version of the landscape, we add the time-interpolated topographic relief and use Landsat optical imagery to provide color. It too is interpolated over time. Over wintertime darkness, we again alter the landscape color and lighting, and the sky, to suggest dim twilight. As springtime returns, so does Landsat imagery. The sun's very low as spring begins, so the early Landsat images are tinged pink with sunrise.
So another type of challenge that we often deal with is large changes in the scale of these data sets. Whether dealing with astrophysics or molecular biology or any kind of physical sciences, objects are often interacting across vastly different scales. So in the previous video, you might recall that we started out by looking at the whole Earth, and then we zoom into this one particular ice cap, and we did that in one seamless camera move. Here on the slide, I'm showing a visualization that we did where we started looking at the Earth, zoomed out to look at the solar system, continued zooming to look at the Milky Way, and then at the very end of it, we're looking at the entire observable universe. This was not one data set. We put multiple data sets kind of together to create this seamless move, but this was without any cuts, no breaks. And this causes a lot of technical challenges like floating point errors. You know, you can't really represent something at such a small scale and such a large scale at the same time. So a lot of creative technical solutions needed to be developed in order to create a shot like this. Because data can be obscenely big, it might not be practical for scientists to capture or create data at regular intervals. Oftentimes, you know, what you want is time to move like the bar on the top, but what we often get is time moving like what you see along the bottom. What this means is that scientists start collecting more data when something interesting is happening, like say over here, maybe there's an explosion and they want to capture that in fine resolution across time. Maybe over here where there's lots of big gaps, maybe nothing interesting is happening, maybe not much is changing, so the scientist is collecting less data there. But in order to tell a story and create a visual that makes sense, you really need time to move linearly. So, you know, this is also challenging and problematic. So let me show a very simple example. Here is a data set that we received for this planetary collision that I introduced at the very beginning. And here time is just moving at two different rates. So you might notice that it's moving kind of more slowly at first and then it kind of speeds up halfway through. So what's actually happening is that the scientist around the initial impact was collecting more data because that was more interesting to her. She was interested in, exactly what's happening at the moment of collision, and then less frequently when it was just kind of in the post-collision phase. So in order to smooth this, let me show you what we ended up doing. Here's the final visualization that we made of this data set. Let me just kind of explain what we're looking at first. We added lighting from the position of where the sun would be, which gives the planets depth and shadows. We added textures to the planets and a background of stars. And we used information from the data, like the type of matter and the temperature at each point, to determine whether it should be a solid, liquid, or a gas. When a point was hot enough to be a solid or to be a liquid or a gas, we also made it light up. We also slowed down the simulation to make it so that we can actually sit back and watch and enjoy it. And we designed a camera move around it that makes it feel cinematic and large. We're slowly revolving the camera around the data and we get right up close to the action. I call this moment it hitting you in the face. That's kind of the effect that we were going for. We want it to really feel visceral and immersive. So this is how we designed it. But obviously, we also retimed it. Time is moving smoothly here. We did that through a process called interpolation. There are many different interpolation methods and techniques. There's some math involved in calculating that, but there are often problems with interpolation that make it appear not smooth. You have to create new data. It increases the size of the data set that you're working with, which is already large to begin with. So this is a problem that we often have to deal with, slowing things down or retiming them. The next challenge is a familiar slide. I mentioned that maps can be represented in lots of different ways, and that is perceptually confusing. It's also technically challenging. There are many different coordinate systems that data might be stored in, many of which might not be natively understood by the software that you're working with. The same data can be represented in different ways, so you often need to translate between different formats to get it into something that'll work with the software or something that is appropriate and works with the visualization and the story that you're trying to tell. It's not only true for maps, it's true for all spatial data, which comes in a variety of coordinate systems and formats. Here are some of the weirder ones that I have come across. Stretched grids, nested multi-resolution grids, kind of random shapes. It can be all over the place. Next challenge is that there actually isn't any software that helps you do this, not one single piece of software. There are kind of two main categories of software, artistic software and scientific software, that each solve part of the problem. Artistic software like Maya, Houdini, Blender, others, these are not exhaustive lists, by the way, really help to get that cinematic look. It makes things look beautiful, helps you design cameras and color and lighting. So, really important in the visual style and communication, but artistic software doesn't understand complex scientific data formats. Scientific software, on the other hand, often does understand the craziest of data formats because scientists are using these tools. They're created for scientists to analyze the data. So the data processing part becomes solved in this software, but scientific tools aren't designed for artists. So you typically can't do something like designing camera, designing lighting systems, making it really look and feel photorealistic or beautiful or cinematic. So we kind of have to use a mix and match of artistic and scientific tools for every project to partially solve the problems and move between the software, do a lot of data translation and conversion to go between them, and also develop a lot of custom software to kind of be connective tissue between the two categories and also to solve some of the problems on their own. So a couple of the tools that were developed at the NCSA where I used to work. We always started with a tool called Party View, which is open source, developed by Stuart Levy on that team. This is really a tool for pre-visualization, so getting a first look at the data. Because scientific data files are very large, they can take seconds or minutes to load into graphic software. So with Party View, we sample down the data so that it fits into memory so that we can render it interactively and just kind of have enough information that we understand the geometric relationships and we can compose the camera frame and dial in the desired data rate and timing of the scene. Another tool that we developed is called Virtual Director. This is what the NCSA uses for virtual camera choreography. And we fly around the data using this 3D mouse called a Space Pilot, which is kind of like a joystick on a video game where we literally fly around the data and can record the path. So here's a screen recording from Virtual Director showing that planetary collision. First we start off by recording this, and then we can kind of fly off from the camera view, and you can see the path of the camera as that curved line and the camera moving along it. We can kind of pause and at any point shift the camera's view and adjust where the camera exactly is looking. You can kind of see that television view in the top right corner. So this lets us very carefully design exactly what's happening when with the camera, what we're looking at, how fast it's going. So a challenge with the artistic software category that I described earlier is that it doesn't understand scientific data formats. So tools like Maya and Houdini and all of kind of the artistic tools expect data to be a uniform, simple Cartesian grid like this. But this is not an efficient way to store scientific data oftentimes. So we might get something instead that looks like this, where it's a stretched grid with a lot more detail here in the center and less detail here on the edges. Or maybe data might look like this. Again, here we have a version where there's more detail in some places and less detail in other places, but it looks very different than the previous one. Same concept, very different type of data format implementation. Or data might be spherical or cylindrical. Doesn't have to have square pixels or square voxels at all. But in the end, if you're working with artistic software, you have to force this data to fit into this type of grid, essentially. So a way to do that is to sample the data, but even that is not a clear-cut problem. How often do you sample it? You might use the smallest resolution if you want to capture all of the data. If you make a uniform grid that has pixels this small and do that, then you will capture all of the data. Excellent. However, that will make the file size like 1,000 times larger. And remember, we're already dealing with very large file sizes. So that's very wasteful since you're spending a lot of memory on areas where there's not actually a lot of information. So typically we don't do that. Another thing that you might do is to kind of choose a medium resolution. So maybe kind of something like this and make the whole grid that size. You can do that and that works fine and wastes less resources, but a problem there is that then you lose a lot of the fine details, which is where the most important stuff is happening. The reason there is more resolution in the areas that are smaller is because that's where the interesting stuff is. So oftentimes, we have to kind of do some kind of combination of the two. Maybe start with one sampling of grid and then as the shot moves on, change to a different sampling and kind of figure out how to smoothly make that transition not visible to the viewer. But we're not necessarily tied to using artistic software. We could use scientific software instead. But as I kind of mentioned before, scientific and artistic software have vastly opposing strengths and weaknesses. So we really want something that does, all of this, can do data analysis, runs on supercomputers, can read data, is artist friendly. You can do lighting and camera and whatnot, but scientific software does half, visual effects and artistic software does the other half. So it requires a lot of programming to create custom tools and middleware to create pipelines that work across these types of software. So the final type of thing I would like to talk about is design challenges. So what is it that actually makes a data visualization cinematic? All types of visualization, no matter whether you're making a bar chart or, a planetary collision, you have to answer questions like, how will you represent the data? What aspects of the data will you choose to highlight? What colors do you use? There's a core set of questions across all visualization, but Cinematic visualization design requires answering all of those in addition to thinking about things like scene design, camera choreography, composition in the frame, kind of more artistic things that come from the world of film rather than technical or visualization related fields. So I want to show you an example of kind of a traditional visualization of a data set versus a cinematic visualization of that same data set to illustrate this. So here's a visualization made by scientists. This is not created for a film. This was created, I think, for a presentation in some conference talk. What we're looking at is an organelle called a chromatophore that lives in bacteria, and it helps the bacteria do photosynthesis, so get energy from sunlight. And we wanted to tell this exact same story with this same data set, but to make it immersive and exciting and understandable to everyone, not just scientists. So here, you can see light hits it and then bounces around, and there's big vocabulary words. I don't know what a quinol and quinone is. You probably don't either. This is not a great way to tell this story to a general audience. So here's what we did. We started out by creating a context. We made millions of copies of this chromatophore shape, and we organized them into the shapes of the bacteria that they are found in. We designed an exciting camera move using Virtual Director, the camera choreography software I mentioned earlier, and we linked it together with VMD, which is a scientific software for rendering molecular structures. We changed scales and we slowly increased the amount of detail that is shown to the viewer. So we're kind of now getting an X-ray view to the inside of the structure. So we really don't just show the data. We design a whole experience that includes cinematography, lighting, color, moving elements, and tells a story. And now, like a minute in, we finally see a ray of light hit this object and begin the process of photosynthesis. After all that setup and creating context for the audience to be able to understand and situate themselves into what are we looking at and where are we and what's going on. So I want to show a few examples of specific filmmaking techniques that we often use. One rule of thumb in cinema and in photography is called the rule of thirds. And that rule states that humans find images more aesthetically pleasing when they're aligned not with the center of the image, but with the 1/3 and 2/3 lines. So here you could see that we placed the Earth kind of at the intersection of these lines. And here in kind of the left third, the screen is pretty much black. There's really not that much going on there. And you might think, well, that's just wasted space. But actually that was a conscious design decision to compose the image in a more visually pleasing way. Another camera technique that we often refer to is putting the camera inside the data box. So here we're looking at two visualizations of similar data of the large scale structure of the universe. Here, what scientists often create is a visualization that looks like this, where you see the entire data set in front of you and you kind of fly around that. We often avoid that. We put the camera inside this box to try to get the viewer as close to the data and as immersed in it as possible. Even though you're not seeing all of the data from the box, seeing it all is not the point. The point is to feel like you're really there, flying through space, enjoying it, and getting a close-up look. Camera lens effects are something that you also see in cinematic visualization, but is never included in traditional visualization. This comes from the world of cinema. The reason you don't see it in traditional visualization is because it actually degrades the image. It makes it blurrier. It makes it harder to see. It makes it less accurate. We have the technology to show this very crisply and accurately, but we actually take the extra effort to make the image worse by making it blurrier. Because this is more cinematic, audiences react more warmly to images with these particular types of artifacts, which mimic how lenses of physical cameras capture light. We often use lighting techniques to bring a dramatic flair to our videos. So starting with darkness and mystery allows you to do a grand reveal of data features in a way that's more surprising to an audience and more impactful than just starting with the data outright. One of the things that's also really important is providing context. So I mentioned in the earlier shot of the biological photosynthesis that we started with the bacteria, which was kind of the larger context of the organelle itself. Here I'm showing a data set without its context. Does anyone want to unmute and guess what it is that we're looking at? It's a little bit hard, and that's kind of the point, to figure out what this is without the context. Any guesses?
The sun.
The sun. Yes, this is the inside of the sun. And this is not what the sun looks like when you see pictures of it from NASA. This is not what it looks like when you look at it with glasses, with your own eyeballs. But this is what the inner 1/3 of the sun looks like. In order to show it in the documentary film that we created, we put it into context. Here we're kind of showing a more X-ray view type look where you can see kind of the fire on the rim of the sun and a little bit more of a familiar context to this data, and then we dive inside of it. So I'm going to break down the single frame into the components that went into it. It involved combining multiple data sets together. We began with a data set of solar surface convection from a scientist, Dr. Matthias Rempel, and his data included surface magnetism vectors, which we rendered as these fiery spikes. The sun's surface was a simulation by Dr. Rempel that came to us as a series of black and white rectangular images. We tiled these images and mapped them onto a sphere and started playing each tile at a different point in time and blended between the tiles so that you couldn't necessarily see the edges as repeating patterns. We used a facing ratio render layer to make the sphere more transparent where it was facing the camera for this X-ray view effect. Around the rim of the sun, we used photographic time-lapse imagery from NASA's Solar Dynamics Observatory, which is a space-based telescope that has cameras looking at the sun. We put the whole sun in the correct context. Now there's a starry sky background, which is a photographic mosaic from Axel Mellinger. And the interior is a simulation by Drs. Mark Misch and Nick Nelson, which shows an important feature inside the sun. These spinning vortices around the equator that the scientists hilariously nicknamed bananas. And here's a visualization made by the scientists where you can see, this shape, which is why they call these bananas. Part of the story that we wanted to tell was that these bananas are rotating, which you could not, just see in the original data set. So we added these rotating streamers around the vortices to really emphasize their motion so that the story could focus on that aspect of the story. So that summarizes the different types of challenges. If you're interested in learning more about this, my colleagues and I have at the University of Illinois developed a 4-week online course, which is free on Coursera called 3D Data Visualization for Science Communication. You can check that out if you're interested in a deeper dive. Thank you. I'll take any questions that you have.
Thank you, Kalina, for your good presentation. I would like to say that we are happy for you to be with us today. I would like to ask some questions, even though some of those questions have been already answered indirectly inside the presentation. I believe these questions would be a good generalization and recap for us, and other students may ask after me. So here are the questions. So as you already said, even though the data came from a scientific base, the visualization might not align with scientific accuracy. So what are the biggest challenges in maintaining scientific accuracy while creating cinematic visuals, and how we can achieve the scientific accuracy? And the other question is, how do you decide which aspects of data sets should be emphasized visually for storytelling? And my third question, are there design principles that you consistently apply when creating cinematic scientific visualizations? So those are the 3 questions I have. Thank you.
Excellent. those are great questions. They're all very different, and each of them could take an hour to talk about. Let me see. I guess I'll start with the accuracy question, the first one. That's actually what a lot of the research of my current PhD is about, because there isn't really a good answer to how do you ensure accuracy. Usually the answer is that you can't. And it's just a matter of what sacrifices you are willing to make, which is why it's so important to work with the scientists, because there's so much complexity in that data that it's impossible to show everything, which kind of goes into your second question too. How do you decide what to show? That is, you work with the scientists to figure out what is the core part of the story. Also with the film director, usually these aren't created to live alone. This is part of a larger film, and that larger film is telling a larger story. And the story of the visualization has to fit the story of the larger film, in which case that kind of helps direct you in terms of like which aspects to focus on. If the film is about I don't know, I can't think of an example. If the film is about, one aspect of the science, then that's the part that you emphasize in the visualization. That doesn't necessarily help with the accuracy challenge. Well, as part of my recent research, I actually did interviews with some visualization practitioners, and somebody said this excellent phrase that they said something like, I never say that this work is accurate. I just say that it's accurate enough. And I kind of love that, because there really is no such thing as accuracy. Design decisions always have to be made. It's just a matter of trying to lie as little as possible, and the ways that you're lying about it, make sure that they're not misleading, that they can be simplifying, that they could be, emphasized. It's like a lie that serves the purpose of telling the truth. Like, I don't know if you remember when you were, if you took like a biology class, you learn about DNA as like 4 letters, right? Like, I forget what the letters are. Let's say they're A, B, C, D. They're not, but I forget what they are, right? That's like obviously a simplification. DNA is so much more complicated than 4 letters, but that's kind of what you learn. And in a sense, that's a lie, right? It's like a simplification. When you take more advanced biology classes, you kind of learn, oh, actually, there's, um, all these other complexities to DNA. And that's kind of an education. It's called scaffolding, where you like teach a simplified version of the concept so that later you can say, actually, that thing you learned about earlier is kind of right, but we kind of lied a little bit. And here's kind of the next step of it. So visualization always, depending on the target audience that you're creating it for, can be more or less complex, more simplified, more accurate. But especially for the general public, which, if you recall, needs to include 8-year-olds, you don't necessarily want to be giving all of the complexity and detail, because they won't be able to understand. I think with that, I probably answered your first 2 questions. I forget what your third one was.
Yeah, of course, you answered it, and the third question is, are there any design principles that you consistently apply when creating cinematic scientific visualizations?
I wouldn't say so. Each project is very different, especially considering that there are different, sciences. So creating something astronomical is going to be very different than creating something biological. A lot of times we try to start from the kind of traditional, understandable norms in that field. Like, for example, to most people, like blue means cold, red means hot, right? Like that's a basic kind of thing that a lot of us have come to understand. So trying to start from these kind of known principles that are just kind of known among the lay public is something that we do, but those are very different depending on the field as well. I think that's part of the fun of this type of work, is that you can't really just repeat the same formula for every project. Every project requires coming up with new solutions and learning a lot of new stuff, creating new tools, because there isn't really a consistent answer that you can apply the same thing to all of them.
Can I ask one question?
Go ahead.
Yeah. First, thank you for the amazing talk. I could watch this again and again. It's so nice. Um, yeah, so my question is like, I know sometimes, for example, if you have some missing data, you can train a model to interpolate in like get more like data. Have you guys used such kind of like techniques, or is it like, okay, we want to preserve the accuracy, we don't want to train in like machine learnings?
We have, and that's actually very controversial. Most
Mm.
other people in this field will tell you they don't do that. I work a lot with NASA, and they're always like, no, no, we don't fill in data. We just show it the way it is. But because a lot of the work that I do is more, I mean, NASA is obviously NASA. Everything they put out needs to be trustable. A lot of the work that we do is kind of more for entertainment and education, or like edutainment. So we have a little bit more flexibility with interpolation and filling in data. So yes, we have certainly done kind of, I don't think we've done it with machine learning, but we've done kind of simple in painting to fill in like holes and gaps in data. Um, if there's like a big gap, oftentimes we'll try to combine multiple data sets. Like if there's something large that we want to put something smaller into, like say put the um, Earth into the solar system, into the Milky Way, into the observable universe. That was like nested data sets that were from completely different scientists that we like put together to create that shot. So if we can, we'll combine multiple data sets so that everything is data driven, even if they're not created by the same science team. But otherwise, for smaller gaps, we do interpolate and fill in artistically as needed.
Thanks.
Can I ask a question? Hmm. Okay, am I audible?
Yes.
Oh, yeah. Okay. While we are on the topic of data, I want to ask a question you mentioned earlier while we were talking about one of the technical challenge, big data. I'm just curious, how is that a problem? I thought in my previous experiences with Emil, the bigger the data, it's the better our model would perform. So how is big data a challenge? Is it related to some kind of storing this data? And how do we solve this big data challenge?
Yes, it's an excess of storage and access. So working with a large data set, if you are, a designer and you want to load in a data set onto your laptop so you can create the look the way that it looks, but it's a 100 terabyte data set that is literally impossible to load onto your laptop, right? Like nobody has a 100 terabyte laptop. So that's one problem. Another is, okay, we use supercomputers at the National Center for Supercomputing Applications. So oftentimes the data needs to be, split up, whether over time or spatially. So kind of figuring out how to divide that data into smaller chunks that can be loaded one at a time and then reassembled, or how it can be split across the supercomputer so it could be rendered simultaneously on many machines is a problem. So it's both on the loading side and the rendering side. It's very difficult to work interactively with large data sets too. So I mentioned we have a pre-visualization tool called Party View where we downsample the data because oftentimes, you do want to see while you're working on it, you don't want to wait an hour for the image to render so that you can see whether or not it worked or what changes you want to make. You want to, change a color and then see if it looks good or not, rather than change a color and then like wait an hour and then see like, no, that looks bad. Let me go change it again. So large data makes things much slower to work with. So you have to come up with creative ways to, downsample it in a way that maintains resolution or split it up so that it can be rendered in parallel. Or yeah, so the storage and the access and the rendering are all challenges due to big data.
Thank you.
There's also a question in the chat.
Yeah, great. So I see there's a question about opportunities and challenges with AI in this type of visualization. Maybe that's an opportunity for me to talk about a project that I'm starting right now. I am in the early stages of a project to create an AI beauty, what I'm calling a beauty filter for visualization. You know how like on TikTok or Snapchat, you can like apply makeup to your face. And it still looks like you, but better. I'm trying to use AI or develop models and tools to let people make like a, simple, maybe more traditional visualization, and then use AI to like click a button and apply a beauty filter to that visualization and have it be cinematic. I think that that is an interesting potential use of AI. Um, since I'm in the early stages of this, I'm trying to just define, what does that even mean for visualization? What is a beauty filter for visualization? How does it work? What does it affect? Kind of more thinking about it philosophically at this stage rather than diving into the technical implementation just yet. But I think that is a really promising direction since a lot of time and effort and money and energy gets spent on um, creating the final kind of beautiful looks. I don't know if you've heard of the 80/20 rule, where it's like 80% of the work is like really easy to do and happens like really fast, and the last 20% of the work happens and it actually takes 80% of the time or something. So, getting it to a stage where it looks acceptable is quick and easy, but like getting that last 20%, or I'd even say like that last 5% is what takes most of the time. And I think that's where AI could come in. I'm less comfortable having AI kind of in the early stages of the process because, there's a lot of hallucination and errors that could be brought in. But I think having it in the later stages, kind of just applying lipstick to the visualization, is a good use of it.
Interesting. Can I ask the maybe last question? I think we are almost 5 minutes out of time. So I think you are the most like one of the person, no, not one of the people that I would say like have pretty interesting journey into this like field. Um, can you tell us maybe how you got involved in this visualization and maybe if you have some advice to students if they want to go into this field? I would like to say something.
Sure. So in my undergrad, I studied computer science and I got interested in computer graphics. In my junior year or maybe my senior year, I took a intro to graphics class and I was like, wow, this is really cool. And I love that. And I thought after graduation that I wanted to go into Hollywood and work on visual effects to like work on the Star Wars movies and like do that kind of stuff because I really enjoyed computer graphics and thought that film and games were kind of the only options. And I'm not a gamer. I don't enjoy that. So I was like, okay, so films, that's what I'm going to do. And before I had a chance to move to LA and start looking for that work, I kind of accidentally stumbled into there was an opening in this advanced visualization lab that I was working at, and I went and I got somebody recommended that I apply there. So I went and I got a demo of their work, and I was like, whoa, this actually is computer graphics, but it's not just like, blowing up the Statue of Liberty for the millionth time in a random movie. It's using computer graphics for good, for science, for education. It's still using a lot of the same techniques and tools, but in kind of a way that helps society. And I really loved that aspect of it. So I never went and followed my visual effects Hollywood dreams. As once I got into visualization, I'm really passionate about it and I stuck with it. And even though my career path was computer science and then graphics, and then visualization, a lot of the people that I work with have very different career paths. Really, the key thing to getting into this field is being interested in the tech, the science, and the art. I kind of had a slide early on that showed those are kind of the three pillars. Um, I know the tech. I'm not a designer myself. I'm not a scientist, but I'm interested in both of those things. I enjoy things that are artistic and beautiful, and I think science is cool and fun. So even though I'm a programmer, like those two other pillars are something that I'm interested in and passionate about. So, if you are maybe somewhere else along that spectrum, or have a different background, but are still interested in all three aspects of that, even if you don't necessarily have experience or expertise in all of them, I think that's what it takes to be in a role like this.
Nice. Thanks so much. I'm gonna stop the recording here.